Good evening, everybody. Welcome to Chem 170 with your host, me, Dr. White. And tonight we'll be going through the review for test number 4, which you'll be taking this coming Thursday. And let's see, I should have it on the screen here. Let me remind you, test number 4 will cover polymers, lipids, carbohydrates. You'll hear me go over that just in a little while. In the review, it has 9 pages, 20 problems. Some of the problems multiple part. In Chem 170, I never have, never will go multiple choice. And the test has 54 points, general knowledge. Hold on, I'll explain that in a second, maybe more in a second. 15 points nomenclature, 36 points for reactions. It adds up to 105, which is five bonus points. Now, why 54 points general knowledge? Well, if I asked you, is my right hand chiral or achiral? Well, that's not nomenclature. That's not reactions. Well, it must be general knowledge. If I ask you to circle all the chiral carbons in a molecule, well, that's not nomenclature. That's not reactions, so it must be general knowledge. And that's why we have so many general knowledge points. Now, if you go to D2L in the lecture section and scroll to the bottom, you may have to press the button or click on the button more. You'll see a file called Test 4 Review. So what you're going to see right now, you can also download. All right, let's start. In polymers, you should know what is a polymer. It's a macromolecule, that means a big molecule, made up of repeating units called monomers. And if you saw my video, which I hope you did, it's sort of like a freight train where you have a lot of the same boxcars. And that's what a polymer is, except not boxcars, but special groups of small units called monomers. All right, you should know there are two ways of categorizing polymers, one by chemical property, the other by physical property. Chemical property, the two types are addition polymer. And you should know that addition polymer is made with only one type of monomer. And you should know examples of that are like your car tires, rubber tires, anything rubber, or saran wrap, which is polyethylene, otherwise known as plastic wrap, but I like using that name. All right, the other type of chemical property you can name a type of polymer is called a condensation polymer. And a condensation polymer is made with 2 or more different types of monomers. An example of that would be this plastic bottle, which is a polyester. I don't have one nearby, but I do have one I got from one company I work for, a nylon jacket. Now, the other type of or type of categorizing polymers is by a key physical property. And there are 2 types. One is a thermoplastic polymer, and that's once formed, like this bottle, once the polymer is made into a bottle, it can be reheated and reshaped. Example would be this plastic bottle or saran wrap. You should know examples also. Now, you should know also the definition of a thermoset. Once formed, it can't be reheated or reshaped. Example would be a rubber tire. If you heat it up, it just burns. It does not melt, so you can reshape it. That's one of the problems with rubber tires, why we have huge waste dumps of rubber tires, millions of them. Anyways, and urethane foam. And that's the foam you're sitting on a chair or a car or other places. And that's in a couple hour or 2 lecture the world of polymers. Now, I could have given, actually, without any problem, I can give a 2-semester, 32-week course just on polymers, but I'm not going to. All right, next we moved into something new, and that's fats and oils. And the first thing is, I talked about lipids. And a lipid is a molecule made from a plant or other living things like you and me that are soluble in nonpolar solvents, but not in water. Now, there are two types of lipids. One is saponifiable, and the other is non-saponifiable. When we're talking about an ester, you learned about saponification of esters. And a saponifiable lipid yields carboxylate anions of fatty acids in the reaction of base with water. And they're called fats and oils. The non-saponifiable lipids do not react or does not react with base and water. And we call those steroids, otherwise known as our hormones. And you should know that a saponifiable lipid is a fat and oil, and a non-saponifiable lipid is a steroid, or the steroids. There's more than one. Now, we're talking about fats and oils, and this is an industry Dr. White worked in for a number of years. And a fat is a solid or semi-solid triglyceride at room temperature. And you should know that. And an oil is a liquid triglyceride at room temperature. If you've ever seen bacon fat that solidifies in a pan after you cook bacon, it becomes a solid. And if you've ever seen olive oil or vegetable oil at room temperature, it's a liquid. Now, here I have the structure of the triglyceride. The general structure right here. And all fats and oils are made up of that triglyceride. The difference is what's our prime and our double prime. And if you notice each one, we have 1, 2, 3 esters. And fats and oils chemists write their ester reverse from synthetic organic chemists, like I taught you earlier. But it's the same thing, I just turn it around. Now, all the chemistry I taught you about esters still holds true, except now we have 3 different esters. And you can have acid hydrolysis of a fat or oil. And as I mentioned earlier, this is how you break down fats or oils in your stomach, because your stomach has H+ hydrochloric acid, which I think is one of the miracles of life that you and I both have cells that produce hydrochloric acid. It's mind-blowing to me. It's amazing. But anyways, if you take an ester, and we'll draw it backwards now, acid and water, get back the alcohol and the carboxylic acid you would have used to make that ester. Well, here you have 3 esters. Ester number 1 gives this alcohol, this carboxylic acid. Ester 2, this alcohol, this carboxylic acid. Ester 3, this alcohol, this carboxylic acid. And notice the 3 alcohols are connected together in the molecule. We have the common name glycerin. And by the way, you make glycerin in your body. Now, base hydrolysis of a fat or oil. Well, you learn base side for test number 3. You learn ester, base, and water gives the alcohol plus the carboxylate anion, the carboxylic acid you would have used to make that ester. And therefore, ester 1 gives this alcohol and this carboxylate anion. Ester 2, this alcohol and this carboxylate anion. Ester 3, this alcohol and this carboxylate anion. I want to say, look behind, what's behind door number 3? For all of you who've seen that TV program. But anyways, I won't. I guess I just did. Now, something I didn't talk about when we worked in esters, but I will now, is steam hydrolysis of a fat or oil. And there are 2 ways to make a reaction go faster. One is to use a catalyst like acid or base. The other is a rule of thumb for most reactions. For every 10 degrees you heat up a reaction, the reaction rate, how fast it goes, doubles. Therefore, instead of using water and acid, if you use hot water, very hot water, you get the same reaction as acid hydrolysis. You take an ester and use steam. Steam is very hot water. Under high pressure, it's much higher than the boiling point of water in your kitchen, much hotter. And you get back the alcohol and the carboxylic acid you would have used to make that. So here we have this triglyceride, any fat or oil, and steam, and you get first ester, this alcohol, and this carboxylic acid, second ester, this alcohol, and this carboxylic acid, final ester, this alcohol, and this carboxylic acid. And I worked at a company where I was the laboratory manager, and on the south side of Chicago, 47th Racine, when I was there, I think they're still there, but when I was there, we used to run this reaction to the tune of about 2 to 3 million pounds every week. Now, the carboxylic acid you get in this or any of the other acid hydrolysis has a special name. Instead of, because it comes from fats and oils, is named fatty acid. Fatty acid is short for fatty carboxylic acid. They just dropped the carboxylic acid. I told you organic chemists are lazy. And there are 2 fatty acids I would like you to know the structure of. The first one is stearic acid. And if I write down, draw the structure of stearic acid, you should know how to do that. And here, instead of writing CH2 16 times, I use paren CH2, close paren 16. And stearic acid has 18 carbons. It's a saturated fatty acid, meaning there's no carbon-carbon double bonds. And here's the structure. Now, there's a mono unsaturated, 1 double bond fatty acid, and that's oleic acid. And it's also got 18 carbons. However, at carbon 9, there's a double bond. So you have carboxylic acid, 7 carbons, these 2, 7 more, and a methyl at the end, 18. And if I ask on a test, draw the structure of oleic acid, that's what you need to do. Now, when it comes to fats, there's 2 types, saturated fat and unsaturated fat. And a saturated fat has only carbon-carbon single bonds. It does have a carbon-oxygen bond because there are esters there. Unsaturated fat has at least 1 carbon-carbon double bond. And that's how you get the oleic acid from unsaturated. And from saturated fats or the chains, you get the single bonds by stearic. By the way, stearic acid is used with paraffin wax, a long hydrocarbon, to make high quality candles. And oleic acid is made into other molecules like esters, oleate, and also stearate that are used in your personal care items like cosmetics and skin creams. Yes, the skin cream or the stuff you put on your face comes from fats and oils. Nothing wrong with that. Now, since Dr. White worked in this industry, you should know tallow is the name for beef fat. Yellow grease and white grease are two types of pig's fat. Now, to make it a real life experience for you, because I worked in this industry, I came up with a general characteristic of this. You should know that tallow, yellow grease, and white grease is that triglyceride. Now, what's our S and our SABO? We look at stearic acid. This part I'm calling our S. And from oleic acid, this part is our SABO. So if we go down here, tallow, yellow grease, and white grease make, and usually it's about a 50-50 mixture, but you have 3 R groups. So how do you make them 50-50? Well, it's more complex than this, but for this class, one's R sub S, the other R sub O, and the third one, you can make either one. And I made R sub S, so I can have my little joke SOS on there, help. And therefore, you should know, if I ask on a test, tallow plus sodium hydroxide and water gives 3 products. What does that mean? Well, tallow and white grease, yellow grease have this structure: triglyceride, triester. Each ester, base, and water gives the alcohol plus the carboxylate anion of the ester it comes from. So the first one would give this alcohol and sodium stearate. This ester gives this alcohol plus sodium oleate. And this ester gives this alcohol, so you get glycerin. And you get sodium stearate again. But I don't ask you to balance it. I ask you to give the products. So there are only 3 different products, even though you get 2 of one and 1 of the other of the carboxylate anions. You should also know the reaction of tallow, yellow grease, and white grease with acid and water, acid hydrolysis of an ester, and with steam hydrolysis of an ester. Now, this is very important. You should know how soap works. Hold on. Hint, big hint. You should know how soap works. And first of all, you should know the structure of soap is a nonpolar tail and a polar head. Now, dirt and grease are nonpolar, and what I don't have down here, water is polar. And the key to this is like dissolves like. And if we had a little dirt particle here on the screen, you have dirt, which is nonpolar. Now the soap, which has a nonpolar tail, that's attracted to the dirt because of like dissolves like. And the polar head wants to stay as far away from the dirt, so it's on the outside. And when this forms, you should know that's called the micelle. And now water looks at the micelle and only sees the polar heads. And water says to micelle, you're polar, I'm polar, let's go down the drain together. And they do. Now, one quick thing. How many of you are familiar with the product micellar water that helps women take makeup off, clean their face? There are no micelles in micellar water. It's soap and other surfactants that once you use it on your face, you create micelles to clean your face. All right. Again, you should know how soap works. And you should know the structure of soap. Nonpolar tail, polar head. Water is polar, dirt and grease, and I better spell grease right. Did I tell you Dr. White was always the first one down in the spelling bee? I probably still will be. All right. So water's polar, dirt and grease is non-polar. The key you should know, like dissolves like. See, it even says on their key. And if you have a dirt particle, you should know how to draw this non-polar tails toward the dirt, polar head on the outside, and that's called a micelle. And the micelle now looks polar to water, and they go down to drain together. Now, a non-sapodifiable lipid is a steroid. And the only thing I'm asking you to learn there is the steroid has this basic skeleton, a 6-membered ring, 6-membered ring, up here 6 and a 5. Let me do it again. 6-membered ring, next to it another 6-membered ring. Up here there's a 6-membered ring, and then next to it is a 5-membered ring. Dr. White's having I have bad hair days. I can have bad drawing steroid days. So 6, 6, 6, 5. And you should know how to draw this. All right, new area, carbohydrates. And watch out, this is a real fattening chapter. All right, you should know what is a carbohydrate. So polyhydroxyaldehyde or polyhydroxyketone or molecule upon hydrolysis, meaning reacting with water and some catalyst, becomes a polyhydroxyaldehyde or ketone. Poly means many, hydroxyl means OH groups. So there's a molecule with either a lot of OH groups in an aldehyde or a lot of OH groups in a ketone, or molecule becomes those. Now, I talked about chirality, and you should know chirality means handedness. It's Greek for that. And a number of years ago, one summer, I actually had 2 students who were fluent in Greek language, and they confirmed that's what it meant. Now, when we talk about objects, there are 2 types, achiral and chiral. I'll never ask the definition, but you should be able to identify what's a chiral, what's an achiral object. And an achiral object is an object with a superimposable mirror image. And if we look at these 2 erasers, assuming there are no marks on them, and I've had a mirror, forget about the marks on them, pretend they're all white. And I had a mirror in between, one would be the mirror image of the other, and you could push them together and all the parts would superimpose. And that would make them achiral. Now, a chiral object is an object with a non-superimposable mirror image. And that means if you have the mirror image, they're not superimposable. An example of that are my hands. Forget if I had the ring on, my right and left hands are mirror image, but they're not superimposable. Notice my center finger lines up, but my thumbs are on every other finger in the wrong place. I line my thumbs up, nothing, my pinkies. Hope you all still call a little finger pinky. Do the people still call it that? I guess so. And your hands are chiral. Now, when we're talking about a chiral object, if you see in a description of the object the word left or right, that immediately tells you it's chiral. Now, before we move on, I got to do this. I apologize. Yeah, my fingers are. All right, everybody watch. Everybody know what this is? You know what this is? A spider doing push-ups on a mirror. Couldn't resist. All right, now next thing I talked about were chiral carbon atoms. And that's carbon with 4 different groups or 4 different atoms, or a combination of 4 different groups or atoms. And you should be able to circle all the chiral carbons. Now, if I were to ask you in this molecule, and if you saw the problem sets in the video when I went through some of them, this is a question I could ask: circle the chiral carbons. If a carbon has 2 or more of the same atom on it, it can't be chiral. Therefore, this is out, this is out. Now, if it's involved in a double bond or triple bond, it can't be chiral. So this carbon is out, and this carbon is out, and this carbon is out. Now, if we look at this carbon, has a hydrogen, hydroxyl group, a methyl group, and this whole thing I'll call R. So that's 4 different things on there. So this would be a chiral carbon. Now the other one is this carbon. Again, it has a hydrogen, a thiol group, this aldehyde, and this whole thing I'll call R. And it has 4 different things on there. And this would be chiral. And those would be the only 2 chiral carbons in that molecule. Next, I talked about enantiomers. Enantiomers are molecules with a non-superimposable mirror image. I'll never ask you what an enantiomer is, but as you saw in the problem set, and here I showed you Fischer projection for the first time, named after that great organic chemist, German organic chemist, Dr. Emil Fischer, who also came up with making how to make an ester, Fischer esterification. Now here we have a carbohydrate, and carbohydrate chemists draw where I normally draw an aldehyde this way, carbohydrate chemists draw the aldehyde this way. These are identical. 3 lines in math mean identical. Now, in a Fischer projection, every intersection of a line is a carbon, but we don't show it. And there's stereochemistry involved in there. And if I asked you to draw the enantiomer of this molecule, I like to put in my mirror. You don't have to. For achiral carbons, you don't have to show the mirror image. And this one and the aldehyde are achiral. But this first carbon, what's closest to the mirror, you'll see first. What's farthest away in the mirror, you'll see farthest away. So here's this. Here, the hydrogen is closest, and the hydroxyl group is farthest away. And the last one, the hydroxyl, is closest. And this would be the enantiomer. And that's the skill you should have. Now, I started teaching you about some monosaccharides, which is just a single aldehyde, polyhydroxyaldehyde. This is glucose. You do not have to know the structure of glucose, but there's a special reaction it undergoes. The hydroxyl group in glucose on carbon 5 is an alcohol. You have an aldehyde. Now, for test 2, I showed you aldehyde or ketone alcohol, acid catalyst. You form this hemiacetal, hemiketal. Now, when two functional groups are in the same molecule and they can react, you don't need a catalyst a lot of the times. And here, this hydroxyl group is this hydroxyl group, attacks this carbonyl. And instead of showing you the Hawthorne structure way of drawing this ring, which most students never get in a one semester course, I came up with a way of showing the world's ugliest oxygen carbon single bond. And here it is. Everything else stays the same. And this is this. And this is important because if this didn't form, you'd never have any carbohydrates like rice, potato chips, French fries, all the things I can't have anymore because they're not good for me health-wise, but they were good. All right, you should know this. If I give you glucose equilibrium, you should be able to write this hemiacetal. If I show you this hemiacetal equilibrium, you should be able to write the glucose molecule. Now, another monosaccharide is fructose. And you don't have to know the structure of it, but I talked about it. And here again, you can have the same type of reaction, aldehyde reacting with an alcohol, acid catalyst. You form the hemiacetal, in this case, ketal. Now, again, on carbon 5, this carbon is 2. You number like IUPAC, this is carbon 5. The alcohol attacks that carbonyl, forms, and I'll put the carbon in so you see this was the carbonyl carbon right here, forms this. And here, once again, you have the longest carbon-oxygen single bond. It's easier to this ring. And you should know, if I give you the structure of fructose, you should know with the equilibrium arrow how to draw this hemiketal. If I give you the hemiketal and the equilibrium, you should know the starting material is fructose, drawn this way. Now, sort of new reaction, but it's a little modification of an older reaction I taught you in test number 2. If we have a hemiacetal or hemiketal, and for this class, I only talked about the hemiacetal, and you react it with an alcohol, you can replace this hydroxyl group with the OR triple prime from the alcohol. So if you start with the cyclic form of glucose, react it with alcohol and acid, you'll form this right here, this acetal. And this is the reaction that allows you to put glucose molecules together to make starch. And you should know it. Now, sucrose, table sugar, is a fructose and glucose bond together. You should know that. Starch is a lot of glucose molecules bond together, and that's called poly, meaning many glucose. And the key linkage between glucose and starch, and also glucose and fructose and sugar, is an acetal linkage. Therefore, if I have sucrose reacted with acid and water, like in your stomach, it breaks down to fructose and glucose. If you eat something with starch and the acid and water in your stomach, it breaks down to glucose, a lot of them. And that's why, and I will ask this ever on a test, what's the sugar in your blood? Glucose, because that's how your body gets it by breaking down starch. So if you had some pizza today with bread in there, you've made glucose in your body from breaking down the starch into pizza. By the way, Dr. White is a deep dish pizza fan, even though I like thin, but deep dish from Uno's or Due's, which I haven't been there in decades, or Gino's East or other places are good. Luminati's. In fact, I grew up about a mile and a half away from the first Luminati's in Lincolnwood. Oh, that was so good when we'd go there. All right, listen carefully. Leaving my class, you should know how to describe with words and a general reaction what happens when you eat a fat or oil. And a fat or oil, the functional group in there is an ester. In your stomach is acid and water. And we describe that as acid hydrolysis of an ester. And the general reaction you learn for test 3, ester, acid, and water, you get back the carboxylic acid plus the alcohol you would have used to make that ester. So you should know when you eat a fat or oil, that's acid hydrolysis of an ester. And the general reaction you should know how to write is an ester plus acid and water gives a carboxylic acid plus an alcohol. Now, you should also know when you eat a carbohydrate, that's acid hydrolysis, and a linkage holding glucose together in starches or in carbohydrates is an acetal. And therefore, you should know when you eat a carbohydrate, you have acid hydrolysis of an acetal. And here, the general reaction that you learned for test 2 was an acetal or ketal, acid and water, get back the aldehyde and ketone plus the alcohol you would have used to make that. And if you remember those 2 twins I had who got upset when I didn't balance things, that's why there's a little 2 there. You don't have to put it. So you should know when you eat a carbohydrate, how to describe that with words and a general reaction. And that's acid hydrolysis of an acetal. And the general reaction is this acetal or ketal, acid and water. Remember, H plus is acid in general. You get back the aldehyde or ketone plus the alcohol you would have used to make that acetal. Once again, leaving my class, hint, big hint. Again, big hint. You should know how to describe with words and a general reaction what happens when you eat a fat or oil. And the key functional group in a fat or oil is an ester. So in your stomach, that's acid hydrolysis of an ester. And here's the general reaction, ester, acid, H plus and water, get back the carboxylic acid and the alcohol you would have used to make that ester. You should also know when you eat a carbohydrate, how do you describe it with words and a general reaction? Remember the linkage that holds glucose together, many units in a starch or a carbohydrate is an acetal linkage, and therefore that's acid hydrolysis of an acetal. And for test 2, you learn acetal or ketal plus acid and water to get back the ketone or aldehyde and the alcohol you would have used to make that ester. And once more, let me remind you, you should know how soap works leaving my class. Soap, you should know the structure of soap, non-polar tail, polar head. water is polar, dirt and grease are non-polar. What is the key? By the way, when I write something in red, it's real important. And the key to how soap works is like dissolves like. And because of like dissolves like, the nonpolar tail of soap is attracted to nonpolar dirt. But the polar head one stays far away from dirt. So you form that micelle. And you should know how to draw the structure of micelle. And then what happens? Water looks at the micelle now and just sees the polar heads and says, you're polar, I'm polar, let's go down the drain together. And they do. So next time you wash your hands, your hair, your face, your clothes, your car, your dishes, you're making micelles. This morning when I took my shower, I was thinking, wow, I'm the only one in Northern Illinois right now who's thinking I'm making micelles. Now you know I'm an organic chemist. And with that, I'm done. Remember, tomorrow night, Wednesday night, I'll have office hour. Wait, today's Monday. Wednesday night, let's start that again. All right, reboot. Today's Monday. Wednesday night from 6:30 to 7:30, I will have my office hour. If you have any questions, come on by. If you can't, email me and I'll see if I can set up a Zoom meeting. Unfortunately, tomorrow, Tuesday, I'm going to be hyper busy, so I won't be able to set up a meeting. But Wednesday, anytime if you need it, I'll be home working on creating labs and other things. But anyways, with that, don't forget, Thursday is test number 4. We'll be doing it online. A week from today, let me look at my calendar. Yep, the 22nd is the deadline by the end of the day, midnight, to hand in your extra credit project. Remember, it's optional if you want to. Before that, email me your project. I'll check it over. And if there's something wrong, I'll let you know so you can correct it. So you can get five bonus points. And with that, been a long night. I will say gehen gesund, which in Yiddish means go in hell. And bye now. I stole that from Granny and the Beverly Hillbillies. Bye.